Mechanisms show the individual steps that reactions take in order to have an overall reaction. So if this is my net reaction, this is the overall, this is what's happening. Ozone is turning into oxygen. The mechanism is going to show the individual steps that happen in between. And the mechanism will also tell me how fast each step is. So mechanisms are individual steps. They're also known as elementary steps. So this is the overall reaction. These are the elementary steps that make up the overall reaction. Unimolecular, or molecularity. Molecularity is talking about how many molecules are involved in each step. So the molecularity of this elementary step is it's bimolecular because there's two molecules. In fact, they're all bimolecular. If I had a unimolecular step, I would have one molecule falling apart. A termomolecular step would be three molecules colliding with the correct orientation and enough energy to overcome the activation energy. So this would be three molecules colliding. Termomolecular steps are pretty unlikely because it's difficult for three molecules to collide at the same point with enough energy and with the correct orientation. So you're almost always going to see unimolecular and bimolecular. An intermediate is something that's going to be formed and then it's going to be consumed. So for example, this BRO forms and then it gets used up down here. And the CLO forms in the second step and gets used up in the third step. So those are intermediates, anything that's going to be produced and then consumed. A catalyst is going to be something that exists in the beginning of the reaction and then it exists again at the end. So it gets consumed and then it gets reproduced to go off and catalyze another step. So I can see I've got bromine to begin with, it gets consumed, but then bromine shows up again in the end. Same with the chlorine. So bromine and chlorine are both catalyzing this reaction. They don't get used up. If a catalyst did get used up, it wouldn't be a very good catalyst because you would run out of it. You can have a homogeneous or homogeneous catalyst or a heterogeneous catalyst. The homogeneous is going to be the same state as whatever it's catalyzing. The heterogeneous will be a different state. A really common example of a heterogeneous catalyst is going to be platinum metal. So platinum metal serves as a surface where other molecules will attach themselves, and then they have a greater chance of colliding. Let's see. Let's look at how rate laws and mechanisms are related. Let's say I'm given this mechanism, and I'd have to be told what the slow step was, and all other steps would be fast. The reason I care about which steps happen quickly and which ones happen slowly is that the slow step slows everything down. So your rate is based on how fast the slow step happens. Everything else is dependent upon that. Let's look at an example real quick. So let's say that I am going to build a brick wall with my students, and I have 75 students. I'm going to have 2 students drive trucks of bricks. So they're going to drop off truckloads of bricks. And then, meanwhile, I'll have one student run these bricks. We're going to build this brick wall in the 3rd story of a building. So I'll have one student run handfuls of bricks. Poor kid, bad job. Handfuls of bricks upstairs. Up 3 flights. Sorry. And then let's say I'm going to have all the other 72 kids are actually going to be waiting, and they'll have all their materials ready to lay the brick. So 72 kids are going to be laying brick. So I'm pretty sure if I have kids dropping off truckloads of bricks, that's going to happen pretty quickly. I don't know how many bricks they can drop off in, per minute what that would get down to, but I'm assuming the 2 of them, it's going to be quite a lot of bricks they're dropping off. This poor kid, I don't know, maybe they can carry 10 bricks up those 3 stories. It's not going to be very much, and they're going to be pretty tired, and it's all the way up, all the way down. So this is happening very slowly. And these 72 kids, I'm pretty sure they can lay all the bricks that get delivered, and then they're going to wait. So these guys are getting backed up. They can drop off their truckloads of bricks, but the bricks aren't making it upstairs any faster than this one kid can run the bricks up the stairs. And then, meanwhile, these 72 kids can't lay brick any faster than they're arriving. So this step gets backed up, this step is waiting. This is the slow step. The rate at which the wall is built is going to be equal to the rate at which this one student can carry handfuls of bricks up 3 flights of stairs. So that's why we care about the slow step. The slow step determines the rate of the reaction. So here I've got a mechanism. Let's go ahead and see what the overall reaction is. I can see A is happening twice, so I've got C is an intermediate being produced and then consumed. I have A plus B forms D. So I know my rate is going to be equal to the K constant times the concentration of A raised to some power times concentration of B raised to some power. And in this case, if this is the slow step, the rate depends on this A. In fact, it depends on A twice. So this is going to be a 2. The B doesn't show up at all, so that'll be a 0. So based on this mechanism, rate equals K times the concentration of A to the second power. So it's a second order reaction with respect to A. Now let's say we switch which one's fast and which one's slow. It's going to change our mechanism. We'll say this is happening fast and this is happening slowly. Well, now I can see that the rate would be based off of B and C. So rate equals the K constant times concentration of B times concentration of C. But unfortunately, I can't say that the rate's based off of C because C isn't a reactant. So I can't tell somebody, hey, if you double the concentration of your C reactant, you're going to double the rate, because there's no C as a reactant. So I have to see what C is based off of. And I can see C is based off of 2 A's. So this is getting backed up. These 2 A's are forming C, and then the C is kind of hanging out, waiting for the B to show up, and as it hangs out, some of the C is converting back to A. It's actually achieving an equilibrium. So that means the rate at which A is turning into C will be equal to the rate at which C is turning into 2A, which means C is proportional to 2A. So I can say this is going to be A squared. Since it's proportional, it's not really equal to, so I'm going to need a new constant to relate concentration with rate. So this will be K prime, we'll just say. So it's a new K, but it'll be yet another constant. So the rate is going to be equal to K times concentration of B times concentration of A to the second power. This is third order overall, first order with respect to B, second order with respect to A. So you can see the slow step is going to tell us, is going to change what the rate law or the rate equation is going to be. Okay, so let's see what the requirements are of a reasonable mechanism. 2 requirements. 1, if you say, I believe this is the mechanism of this reaction, you're going to need 2 things to happen. The first one is your steps have to add up to the overall reaction. Otherwise, how could that possibly be the steps that occur if they don't add up to the overall reaction? Second one, the rate law indicated by the mechanism has to match the empirical rate law. And the empirical one is the one that you found in lab. So if you find in lab that when I double the concentration of something, I double the rate, that's first order. And when I double the concentration of something else, I quadruple the rate, that's second order. And if I double the concentration of yet another thing and the rate doesn't change at all, well, that thing's going to be a 0 order. So whatever rate law you get from that mechanism, it has to match what you figured out in lab. So let's say I've got, this is my overall reaction. 2A plus B goes to C. And I'm going to have the rate law, rate equals K, times A to the A's first order, B's first order. Let's go ahead and check and make sure, first of all, if these things add up to the overall reaction. If they don't, they're not going to work. So here I can see that I've got B canceling out, so I've got rate equal, well actually here I've got 2A plus B goes to C. Well, that matches. So the overall steps add up. Let's go ahead and check what the rate law would be. So I know rate is based off the slow step. So that's equal to these 2 B's. And one of the B's is going to be equal to the 2 A's reacting. So here I can say rate is equal to K times, well, I would put B squared, except for instead I'm going to say B raised to the first power, and then that other B is going to be proportional to 2 A's, because this is going to be in equilibrium. That's forming and these are turning back into it. So A squared. Okay, well, that doesn't work because the rate law is supposed to just be A is going to be first order, B is going to be first order, so this is not an option. Let's check this one. Let's go ahead and add up the steps and see if it matches the stoichiometry of the goal reaction. So I can see I've got 2 A's. This D intermediate is going to cancel out, so it all adds up. I've got 2A plus B forms C. So it adds up correctly. Let's go ahead and check the rate law. So this is the slow step. That means all of these guys are going to be involved in the rate law. I can see that D is proportional to A and B. So I have rate equals K times the concentration of A. And I would put in the concentration of D, except for D is not a reactant. So instead I'm going to say, well, D is proportional to these two being used up. So that's going to be B and A. And if I have A to the first times A to the first, well, I can say A to the second. Again, it doesn't match the rate law, so this is not an option either. Then, let's look at this one. If I add up the steps, I can see that I have the wrong reaction because C is canceling out, and I end up with A plus B plus another A makes D. So 2A plus B goes to D. So that doesn't work. Although the rate law would have been nice because it's based on the slow step. This guy's rate law would be rate equals K times A times B. Concentration of A times concentration of B. So it matched the rate law, at least we have that, but the overall reaction doesn't work, so this is not an option either. Okay, so here, let's see if this one will work. I have the D is going to cancel out because it's an intermediate, and overall I have 2A plus B makes C. And when I look at the rate law, I can see that A shows up once in the slow step, B shows up once in the slow step. So the rate law for this one, or the rate equation, is rate equals K times the concentration of A times the concentration of B. All right, the overall equation matches the steps, and the rate law that I determined in lab matches the rate law that my mechanism is showing. So this is a reasonable mechanism. Yay!